So the facility at Mount Hamilton has quite a history to it. It was first created in 1888 with the construction of what's called the Great Refractor. It was the largest telescope in the world at the time and was used for many discoveries. I think the moons of Neptune were discovered with it. In 1959, the 120-inch Shane reflector was commissioned. That was not the largest telescope at the time, but it was instrumental in discovering a lot of the properties of the expanding universe at the time. It was the second largest after Palomar, yes, after the 200-inch, which was commissioned in 1949, I think. And then the Keck 10-meter telescopes were as a pair in 1993 and 1996. And I'll tell you a little bit more about those in a bit. Also the world's, and presently the world's largest telescopes. Oops, too many. We all started when James Lick, who was a railroad tycoon in the end of the 19th century, gave $700,000. That's what it took to build the observatory, build all this. They'd shave the top of the mountain off and everything. So it was the first permanently occupied mountaintop observatory. At the time, people put observatories in the middle of cities. And it completely embraced photography, the actual use of film instead of your eye, and became a premier observatory. You can see the horse and carriage here. This is almost repetitious, but UCO is a UC multi-campus research facility. In other words, the observatory, even though it's here headquartered on UC Santa Cruz, is actually servicing the entire 9-campus community of the University of California. We happen to have the headquarters in Santa Cruz. The headquarters used to be on a mountain, but when this campus, Santa Cruz campus, opened, the headquarters were brought here. The mission is to develop and manage the astronomical and optical IR facilities of UC, so it supplies a support role to the astronomy departments at the whole UC. And astronomers, and to carry out forefront research in astronomy and astrophysics. In addition to that, and going along with that, we're also carrying out forefront research in the development of instrumentation, and that's what I want to emphasize, and that's one of the reasons I'm here. These are some of the prestigious astronomers that have been involved with the observatory in its heritage here. You see Professor Andrea Ghez from UCLA. She's been looking at the Galactic Center. We've had 22 faculty, or 22 members of the National Academy of Sciences, 11 Packard Fellows, 33 Sloan, a couple of Nobel Prize winners, Kavli Prize winner, Jerry Nelson. Here's Jerry Nelson standing in the Oval Office with President Obama. I'm sorry, that's so low on the picture. The facilities, this is an example of the facilities. This, I think, is the illuminizing of the 3-meter, the 120-inch telescope primary mirror. That's the primary mirror with all the coating stripped off, and they're about ready to recoat it with aluminum. We have complete facilities to equip and operate the Lick Observatory, including the coating chamber for that thing. We also have complete facilities here, which I'll tour you through, that actually have built several major instruments for the Keck observatories, as well as some of the optics for the Keck telescopes. We have a laboratory for adaptive optics that I run, which carries out basic R&D for astronomical adaptive optics. We have a coatings facility that I'll show you, which has recently been refurbished to high quality. And of course, the scientific staff that's just world class. This is a little snapshot of my lab. This is me in the back scratching my head because this esteemed visitor was asking me tough questions. So we have an optics lab, the lab for adaptive optics, a full engineering group, an instrument shop, an electronic shop, detector laboratory, forefront in the development of CCD detectors for astronomy, a programming group and administration and so on. UCLA down in Southern California has the infrared laboratory led by Professor Ian McLean, and he's been a principal developer of large format infrared instruments so that we can take CCD-like photography, but in the infrared wavelength bands. And this is a sort of a fisheye lens view of the present instrument that's under construction in the high bay of our shops. It's called the Gemini Planet Imager. It's actually this blue thing over here. These are in a clean room area, and it's presently under construction, due to be finished in on the order of 6 to 8 months' time frame, and shipped to the Gemini South Observatory, where it will be actually imaging planets orbiting around nearby stars, actually taking pictures of those planets, even though they're about 1 billion times dimmer than the star. So the trick is blocking the starlight and getting the planet behind it. LIC has been involved in technology development for instrumentation. I think this picture here shows the laser guide star up on Mount Hamilton. We have standalone programs in science, supportive Keck programs inside Keck Telescope. We are a partner with the Keck Telescope. We're a partner with Caltech in running the Keck telescopes. We have undergraduate and graduate education in astronomy and astrophysics, as well as in instrumentation. I have several PhD students who are working with me. And we have a substantial public outreach and education program. This is one of our public outreach programs, I would call it that, I guess. We've been doing some high-profile programs. This one happens to be a completely robotic telescope that's up on Mount Hamilton. It's designed to view supernova, swing over and see when a supernova has been discovered going off. It can swing over and take the whole time series of photometry needed to characterize an exploding star. And this is a newest addition to the mountaintop called the Automated Planet Finder. It's not imaging the planets, it's only imaging the reaction of the star to the planet orbiting around it. It's called radio velocity searching, but it has to have a very high precision spectrometer. That's just been commissioned. It's a dedicated robotic telescope, 2.4 meters in diameter. So here it is. It's brand new, and so the observatory up there has vital programs ongoing right now. This is you'll probably meet him if he's in the shops here. This is Dave Hilliard, who's looking at one of the optics that went into that spectrograph. And we have the abilities there to polish and coat all those optics. Adaptive optics, again, we were the first, the Shane telescope, and here's the guide star if you can see it. We just missed the moon, but shooting this way. It's basically the first laser guide star adaptive optic system. There were adaptive optic systems that used stars themselves, bright stars, as a reference point for correcting for the atmosphere. A little bit background, adaptive optics. The idea is to remove the twinkling and blurring of starlight caused by the Earth's atmosphere. I think Claire is here, right? So she gave the talk on this. In order to do that, you need a reference source that's effectively a point. Looks like a star looks like this. But it needs to be bright. If you're off looking at a galaxy in a dark part of the sky where there's no natural stars, then you need to create your own. And that's what the laser does by resonating. All of this actually is just scatter from the light in the air. We ignore that. It's scattering off of some sodium atoms that are in the upper mesosphere, actually the mesosphere thermosphere interface. And this is one of our technicians working in the laboratory to build an adaptive optics instrument that was used as a technology test bed for some new technology for deformable mirror technology for adaptive optics, and we'll see some of that in the lab. A little bit of history on the Keck telescopes. Up until 1990, or 1984, or whatever it was that I had, that was the first date of the Keck telescope. The largest telescope was a single monolithic mirror 200 inches across. To make them any bigger than that was starting to get almost an impossible technological challenge, and to keep them steady enough so that they could still form a coherent image of the starlight. So what Professor Jerry Nelson and this is Terry Mast, who worked with him on this project, developed was an ability to make a large single mirror out of many segments of mirrors and to phase them together to the precision of a wavelength of light and to control them as you pointed the telescope around on the sky. It was not clear that that would work at first. He faced a lot of challenges just to convince people to do it. However, it was, and here it is. This is the primary mirror of the Keck telescope with its 36 hexagonal shapes, 1.1 meter across diameter, 2.1 meter across diameter telescope segments. So that was quite a feat and allowed you to build a 500-inch telescope, or now we call it 400-inch, I guess. Now it's 10 meters. We do it in meters now. This is what one of the segments looks like, uncoated. It's on a handling cart like this. They are regularly changing these segments in and out to recoat them to keep the mirror surface pristine. There's another picture, bird's eye view, looking in through the dome slit. So this is the entrance slit of the Keck 2 telescope, and here's the aperture, and you can see the sky reflected in the back. I think a little arrow will come down and point to a person standing on the edge of the slit, so you get an idea of the size of that. The Keck Observatory has been extraordinarily productive in optical and infrared astronomy. Acceleration, one of the biggest discoveries is the acceleration of the expansion of the universe. We know from Hubble's law that the universe is expanding at a rate proportional to the distance away. To find out that it was accelerating was quite a game changer. It's through its spectrometer, it has discovered a majority of the extrasolar planets that have been discovered so far. I'm not sure if that's still a true statement with the Kepler mission now discovering, the spacecraft that's discovering them. Has discovered gamma ray bursts and history of star formation over cosmic time. So it's a very big aperture, so you can look very deep into space, very earliest phases of the universe. In fact, the Hubble Deep Field was then followed up with pictures taken from the Keck telescope that did spectrographs like this. This I'll get to in a minute. It's been productive in terms of science, so this is patting ourselves on the back. The Keck telescopes produce more science papers per telescope than any other telescope in the world. Excuse me?
Is that only ground-based telescopes, or is that
I think these are only ground-based, yes. Okay.
3 times as much as more. 3 times more expensive, though.
Oh, much more.
Yeah, we could get into that. Cost per dollar per, okay.
This doesn't show us the citation rate. The citation rate for Keck is more than twice that of the next, which is
Okay.
BLT.
Yeah. So citation means is a measure of the importance of how that, how important was that paper to the science community. So that's a real, that's a better measure. These are Mike Bolte's graphs. Blame my director. This is a team standing beside the high resolution spectrograph that's at Keck. I'm sorry, no, this is, I think, the Deimos spectrograph. This is a wide field spectrograph. And these instruments, both the wide field and the high resolution, were built at UC Santa Cruz. And a couple of other instruments were built at UCLA. So, so where she is, right here. Okay, I didn't even see her at first. Sandy Faber. I think there's a better picture of Sandy in the.
The Deimos spectrograph, the most powerful multi-object spectrograph.
So what it does is it looks at lots of stars and spreads their spectrum, but it looks at lots of stars at once.
What's the name of Deimos spectrograph?
I'm sorry?
What's the name of the instrument?
It's called Deimos, which is deep. Ooh, Joel, you help me. There we go. Deep extragalactic imaging multi-object spectrograph. Okay. More pictures of Deimos going into place, I believe. This is the slit mask, I believe. So now something I know a little bit more about, adaptive optics. So by measuring the blurring of the atmosphere several times a second, we have this feedback control loop that's happening at kilohertz rates and deforming a mirror. This mirror is inside the adaptive optics instrument, but it's essentially at an image of the main mirror of the telescope. So it's as if you're moving the main mirror around to take up the difference in the optical aberrations of the atmosphere in real time. And that's been extraordinarily productive in terms of producing high-resolution images. This is another beautiful picture of the laser going out of the Keck 2 dome. Both Kecks now have lasers, by the way. This is a picture of Neptune if you look through the backyard telescope. There's two pictures of Neptune, actually. This is when you look through Keck. This is at one time a day. This is another time, or another time. You know, you see these clouds evolve on the picture. But another extraordinary thing about this is you notice that Neptune has rings, and I believe that Keck's the only telescope on the ground, or at least at the time when I saw them doing it, it was the only one on the ground that could see these rings. As well as the ring around Jupiter, is a ring around Jupiter. But not only do you see the ring, you see mini rings. There are 10 or 12 rings in here that you can distinguish with this instrument. And then those have been characterized, and they've found the shepherding satellites, and they've looked at the twisting of the rings and all kinds of very interesting stuff. This is the center of the galaxy. This is where the black hole of the center of our galaxy is located, and these are the stars that are around it. This is what it looks like with adaptive optics at Keck, and you can see right here, there's a group of stars clustered around this supermassive black hole. And in this picture, okay, is put together by Andrea Ghez that shows an epic history of those stars orbiting around the black hole, something you could not possibly think of doing without adaptive optics. It's pretty amazing. So you can tell the mass of the black hole from that. You can tell exactly where it is. And you can trace all those orbits. This is the first image of extrasolar planets. These are actually planets of this star, which has mostly been blanked out and canceled, and there's a few artifact residuals of this star. The star, like I say, is about 1 billion times brighter than these planets. But we discovered there are now 4 that have been discovered in this HD 8799 system, also with the Keck adaptive optics. We were the first 3-meter laser guide star AO system at Keck, at LIC. So LIC was a sort of the prototype for the Keck system. We formed the Moore Foundation and Laboratory for Adaptive Optics with a grant from the Moore Foundation. And we ran for about 6 or 7 years on this grant and built up quite a facility here. That's it for my part of the talk. I'm going to give it to Raja, who will talk to you more about TMT. The 30-meter telescope.